I'm delighted that after two 10-hour days, dawn to dusk, some of you are still here. And I did think that, given this title, Future Prospects of Cryo-EM, if necessary, I would just be able to say, the future prospects are good. Shall we go straight to dinner? But, you know, I could tell you'd be very disappointed if that was. So, what I've got is some slides that go back about 20 years and go forward about 10 years. So that gives you a kind of a, on either side of today. So, 20 years ago, Tim Baker and I wrote a review for the International Tables for Crystallography, trying to explain to the crystallographers what the prospects were for cryo-EM. And we picked these four structures. This is the year roughly 2000 it was written. Single particles without symmetry, E. coli 70S ribosomes, Joachim Frank's best structure at the time, which was 11 angstroms with small and large subunit, and, you know, a long stretch of double-stranded RNA, some tRNA, and so on. A sub-nanometer structure of the hepatitis B virus cores that Bettina Botcher did when she was a postdoc with Tony Crowther in Cambridge. This was the first single particle structure below 10 angstrom resolution in 1997, and it was actually years before there was a second one. Then there were filaments. The great thing about electron cryo microscopy, you can make specimens of anything, you know, whether it's tomographic bits and pieces of cells or sort of junk, as Peter was saying, or, you know, single particles that are identical but with no symmetry, with symmetry. These are a helical, one-dimensional crystal, and this is thin filaments in muscle decorated with myosin. Ron Milligan's work at 30 angstrom resolution by doing plus and minus treatments with and without tropomyosin, myosin. You can build up a model even though it's at very low resolution. And then there's been about a dozen 2D crystals that are essentially crystallography done with electrons. And for years, we worked on bacteriodopsin, but Werner Kuhlbrandt worked on this light harvesting complex from green plants, and that was the sort of second near atomic resolution structure. But the same microscope was used to take the same kind of images, and at this stage, just different computer programs were used to analyze it. And you got different resolutions. The reason that the 2D crystals work really well was within that area, there'd be maybe 10 or 20,000 molecules all in the same orientation. Whereas here, you have to find the orientations, same here, and then here, there's a helix, you have to find the parameters and so on. So that's how it was, but it was clear from earlier work that Jacques Dubochet had done that it was going to be a wonderful method to use for structural biology. And this was from a review that Jacques Dubochet wrote in 1988 to describe work they'd done over the previous 7 or 8 years, in which they took an EM grid here, held in a pair of forceps. You put a drop of liquid on, blotted it, and then dropped it into liquid ethane at the temperature of liquid nitrogen. And that was the method that was developed by Alistair McDowell and Mark Adrian, who were scientists in Jacques' group at the EMBL in Heidelberg from about 1980 onwards. And my understanding is that Alistair McDowell was the one who had the bright idea of using liquid ethane just above its freezing point so that you could very rapidly freeze the thin film of ice. And Mark Adrian was the one who invented the piece of blotting paper that made the thin film. And actually, most people, that's exactly what they do still, although people are beginning to move towards more sophisticated ways of making thin films of liquid with the molecule in. And one of the earliest pictures, going back a bit further, on the front cover of Nature in 1984 was this picture of adenovirus from Jacques' group. And we had a PhD student in Cambridge that Linda Amos and I were using. We were trying to work on tubulin, sort of semi-crystalline objects and so on. And we sent him on a course that Jacques had organized in 1983-84. And when he came back, he resigned from our project and said, cryo-EM of single particles is the future, and that's what I'm going to do. So he then went off to work with Barbara Pierce and Tony Crowther. We lost him. So our first student realized that cryo-EM had a great future, you know, before we did. So Jacques, having taken this in 1984, he wasn't so hot on computing, so it took till seven years later until Phoebe Stewart, who was a postdoc at EMBL with Steve Fuller, who analysed images like this and got a structure at about 35 angstrom resolution using 100 kV electron microscopes with tungsten filaments and film. So you were limited entirely by the technology. The cold stages were cold, but not very good. They would vibrate and drift, and so the resolution was limited. And when you analysed the images, the reason they were limited is that the Fourier components, as you went higher and higher resolution, got weaker and weaker. And that's described by this blurring factor, B factor, which has been used since Debye-Waller factor. They had B factors of 2 for sodium chloride crystals, but this is 3000, and that's why you're limited to 35 angstroms. It means that the Fourier component at this resolution is getting very weak, and you're just stuck at that resolution. And that's where it remained until 20 years later. Hong Cho's group at UCLA took similar pictures of adenovirus, and now you can see a lot more detail in it. And when you analyze those images, that's the same image analyzed, you get now, instead of 35, 3.6 angstrom resolution. This is still on film, but they had a higher voltage microscope with brighter sources, stable cold stages, so entirely technology improvements. They also used a lot more images, whereas originally Phoebe Stewart had maybe 10 images. They had 1,000 sheets of film with pictures of these adenoviruses on it. And when you look inside at the density of one of the subunits, you can see you can resolve the strands of the beta sheet consistent with this claimed resolution. And in parallel, of course, the blurring factor that describes the fading of the Fourier components has dropped from 3,000 to 300 square angstroms. And so that was the early stages. It was very promising. Before this, and actually 10 years after Dubochet developed this plunge freeze method, our group and myself, we were entirely focused on doing electron crystallography. But in 1995, and I thought I'd show one slide from my own efforts, I was asked to go to a meeting where they wanted to build an X-ray microscope, and we knew that electrons were much better than the radiation damage. But the people at the meeting didn't know that. So I wrote this review and ended up trying to calculate what, from first principles, would be possible once all the problems that were still confronting us in the EM area had been solved. And that's this table, which you shouldn't worry about the actual numbers, but it's a figure in a review 25 years ago. And so the idea was to look at the structures people had been working on from, say, large viruses like the adenovirus, smaller icosahedral structures, ribosomes, big enzymes, small proteins, very small proteins like cytochrome C or lysozyme, and work out, if you take an image limited by the radiation damage in the EM, how much signal would you get, how much noise would you get from the limited exposure, and then work out all these columns. And the key things are, there's this line here on the column says, can you see molecules above the noise level? Because there's a noise level, and if they're too small, for example, if you had a protein consisting of 2 amino acids, it's 2 or 3 water molecules, you definitely don't see it because the noise is too high. So it turned out it was about 7 or 8 kilodaltons between a small and a very small protein, and then you can see it as a little black dot above the noise level. And then, of course, to find its orientation so that you could calculate a 3D structure, you need more data from the image of that particle. And that's that second line here. That came out about 35 or 40 kilodaltons. So we said, oh, yes, it looks pretty good. People have only been working on things that are 3, 10, 20 megadaltons. But this says maybe you can go down and do a lot better. And then the final column was calculating how many images so that you could get the signal above the noise level, and I'll come back to that. It was about 10,000 in those days. So then we said, okay, we're going to stop doing crystallography, we're going to start doing single particles, and then try and address the problems that were preventing this from working. And one of them was, alongside all the hardware developments, was the detectors. And so we got involved, as others did, in developing better detectors. And this is a picture of when these new direct electron detectors first became available, about 2012, 2013. There weren't many people working on it, but film is the black line here, and this is detective quantum efficiency, which says what proportion of the electrons that are potentially recordable in the images do you record? And it turned out we were measuring about a third of them because of various things. The film didn't absorb them and so on. And then, of course, the electrons go into the film and they blur a bit. And so at higher resolution, you would lose the power of the Fourier components. That's why the adenovirus was limited in resolution. So the three companies that made these direct electron detectors, which was Gatan, FEI, now Thermo Fisher, and a little company in Southern California, Direct Electron, they're all better than film, but all of these new detectors, when you take a picture, it comes out as a movie. And one of the problems with film was you get one image, it takes you some hours to develop, and then you have to look at it, throw it in the bin usually, but digitize it. But during the exposure, if anything moves or the specimen gets charged up, it blurs the image. The great thing about these new detectors, they have a movie so you can sort of unblur it. And so with that, people started to take pictures, and they turned out very well. People started to determine structures, and then we would get emails from people saying, we've been starting to do cryo-EM, and we haven't got very far. Here is an image we've taken. Is this good enough? And usually it would not be good enough. It would be a pile of crap, really. So we were very tactful, of course. We always replied and said, this is very encouraging. But basically you have to try harder. And then we would send them an image of something similar in size and contrast to what they were trying to do. So that, and you'd say, you know, please try and do something like this, and then you can proceed. And then after a while, so many of these came, we got a little bit tired of sending the tactfully encouraging emails. So Vinoth Kumar and I, and I'll show some of his work later, decided we should write a review and put really nice pictures that were of the type you would need to solve the structure, and then we could just refer them to the review. And there are these now. So these are not like many of the images that you see from cryo-EM, in which you wonder, how on earth can that ever give you a structure? We'll look at some of those in a moment. But these are really nice ones. So the first one was this pyruvate dehydrogenase that Richard Perham's group had made. And this is a specimen made by Peter Rosenthal in the year 2000, when he was when we were thinking of how to get involved. And the images then were maybe 8 or 9 angstrom, 10 angstrom resolution. The paper was published 2003, but the specimens live on, and we still have them. So you can thaw them out, and with the latest technology, take new pictures. So this one was taken with the new detectors. And so now, here is the ice, frozen by the Dubochet method. Here are two-fold views, let's say 5-fold views, 3-fold views, and this is the carbon film. This is a hole in it, and there's no defects, there are no deformed particles. It's really nice. And it's 1.5 megadaltons, so it was a big one. And so then we have this theory saying, how small can you go? So the next 2 or 3 pictures are different as you're coming down in size. So the next one is 1 megadalton, and this was another specimen, no symmetry now. And one of the reasons we got involved with this is that we said, there are lots of people in the world doing cryo-EM on ribosomes, and we're never going to work on ribosomes by cryo-EM in Cambridge, so we need something else with no symmetry. And this is mitochondrial complex 1, which Nico Grigoriev started to work on. He went to visit John Walker, purified it, took images, and in 1998 published a 22 angstrom resolution picture of this exact molecule. And then things remained in hibernation for 15 years or so, and when people would come along and say, what should they work on? I always suggested mitochondrial, but no one took it up, and Nico stopped working on it. So around about 2013, Judy Hurst, who's in another MRC unit in Cambridge, she came back, she said she'd heard about this EM, and she brought this specimen, and I'll show you a bit of it later. So it's 45 different polypeptides, it's a membrane protein in detergent, and 15 years earlier it could only be done to 22 angstrom resolution, but now, as I'll show you in a minute, there are really good maps of it. And also you can see by eye, you can see that it's an L-shaped molecule when you look at it side on, but you can see end views and so on, all the different views, but with no symmetry. So then coming down, another factor of 2, this is beta-galactosidase, and this was another specimen we'd started on back in 1997, couldn't get a map. So 2011, we first got something that we were convinced by on film at about 12 angstrom resolution. Now, this is with the new detectors, and if you look, you can see each molecule, and by eye, you can see the 4 subunits. It's a tetramer. It's lacks Z from the first operon. So here's 4 subunits, and you can, if you look up, you can see the other views. Here's a sort of C-shaped view, which is a 45-degree tilt. You can see by eye the particles, you can see by eye the orientations, and then you can get much better structures than you could get back when you were doing it on film. And then one more, this is human erythrocyte catalase. Again, it's been blotted in the middle, and so this is just pure buffer. And you can see now, at this level of exposure, there are little black dots, and that comes from the noise level, from the stochastic electron exposure level. You know, say 20 electrons per square angstrom, so 20, each pixel will be 20 plus or minus the square root of 20. So you get noise and you get little black statistical dots. But these are 220 kilodalton human catalase, so it's a tetramer, and they've been squeezed out by the Dubochet blotting procedure, and you get these little ribbons here, where they tend to aggregate into the same orientation, but a bit further out, the ice is thicker, and then you've got all the different orientations, and a bit further out, the ice is very thick, and they're on top of one another, and then here's the carbon film again from the hole. So again, 200 kilodaltons, by eye, you can see the orientations. And another factor of 2 is, this is a Mark Pepys human serum protein called pentraxins, CRP-SAP. It's homopentamer, and if you look carefully, you can see these little rings of 5 here, and then edge-on views. There are not so many in between, but you can see, again, by eye, you can see the orientation 100 kilodaltons. And so it consistent with our hand-waving theory and so on. And then the last one we took in this review that Vinod and I published was human hemoglobin, because we always thought, even though Max had died before cryo-EM started, we always felt he'd be looking down and be very pleased if we could do the structure of hemoglobin. But we said, okay, this is a bit too small. You can see the particles, and they're quite big black dots, and there is some shape to them, but we thought this was too small, and that's what we wrote in the review. But as I'll show you, one of the students from Max Planck in Martinsried didn't pay any attention to other people's, and she managed to get a hemoglobin structure, and I'll show you. So now I'm just going to show you a few examples of structures, 3 or 4 of them, that show you what the power of the cryo-EM single particle work as it emerged with all the new detectors and the new instrumentation and so on. And the first one is from the work of Alexei Amunts, who was a student here in at the Weizmann, and then came as... Sorry. I've made a big boo-boo, yes. Sorry, Nelson. The reason I'm confused is I understood...
He should have been in Weizmann.
Yeah, no. But I understood the Weizmann tried to recruit him back, and I assumed that must have been where he came from. So anyway, Alexei came to work with Venki, and the idea was to find out the structure of the mitochondrial ribosome. And of course, there've been lots of ribosomes from Venki's work before that. But the difficulty is getting ribosomes out of mitochondria, out of beef heart. Apparently, there aren't a lot of mitochondrial ribosomes. And when you try to purify them with the goal of crystallizing them, there's a lot of cytoplasmic ribosome impurities. Anyway, this was an image. And so what happened is Alexei's beavering away for a year or two. And in parallel, Georges Scherez has got a new postdoc, Xiaochen Bai, who'd come from Tsinghua in China and had been really well trained how to make grids, how to make specimens. He was a cryo expert. And Georges had been writing new programs rely on to make the methods better and the detectors. So there was a coincidence of these 3. Xiaochen, new detectors, and so on came. And this was one of the first specimens they started to look at. And they put it into Shor's program Reliant, and you get this average structure of all of them. But one of the great things about all the new softwares is you can say, I think my specimen might be impure. And you just say, I think I'd like 2 or 100 different structures from the same data set. And here they picked 6. And as you can see, it's sorted itself out just by cycles of refinement against all the particles, against all the models. And 4 of them turn out to be either intact mitochondrial ribosomes, 2 of them, or the large subunit with the small subunit missing. And then about 1/3 of them are the cytoplasmic ribosomes that were not. So it's not surprising that you can't crystallize such a thing. And there were others that didn't know. So by then selecting the particles that fall into the classes that you believe are what you want, you can get a better structure than you can get from having them all in mixed together. And then one of the other facilities in RelyOn is that you can use part of the structure to focus on it, to find the alignment of the position and the orientation of it. So you can take the large subunit, refine on that, and if you've got any motion, say ratcheting in the ribosome, then instead of having a blurry image of the whole thing, you get a sharp image of the bit you're focusing on and a more blurry image of the other part. And then the same data set, you can focus on the other part and get a sharp image. So you can look around, and you've heard talks in the meeting about that. So when they did that, they got a really nice map of all the proteins and all the subunits and so on, and ended up with this structure. And some of the nicer parts of it are here. So this is a nice little piece of Watson-Crick double helical RNA, and here's a Watson-Crick base pair, an alpha helix, and a couple of loop regions with what's believed to be a magnesium ion. So that's a very good example of the power, because it's a mixture of states, it's got flexibility, it's got all the things that were really problems in structural biology. So the second one that I'm going to show you is another one that involves Xiaochen Bai and in Shores' group. And Xiaochen came from Tsinghua, and he knew people there. In particular, he knew Yigong Shi's group had been working on this protein, gamma secretase. And so there was a collaboration. So this is Xiaochen, Shores Sherez, and Yigong Shi's group who were making the protein, sending it to Cambridge, making these grids. And if you look at this, this is not one of these beautiful pictures. It actually looks dreadful. But when you put it into RelyOn and you do 2D classification, just like the 3D that I showed you with the ribosome, you get classes like this, and you can see the membrane part with the detergent, part that's the hydrophilic part sticking out, and then they got a structure, and with more work, quite a lot of work, 1 million particles or so, they got to 3.4 angstrom. And when you cut out the different densities, you can see there are the 4 different proteins. In the membrane, there are 20 transmembrane helices. Only 19 of them show up at high resolution. There's one a bit blurry, but when you pull them out, they look really nice with side chains sticking out and so on. And this is the nicastrin, the green subunit, which is mostly beta structure, but 1 transmembrane helix. This is the transmembrane helix. Here are the beta structures. And in some of the surface loops, there is glycosylation, and they could even see some of the sugar residues. And then in the detergent belt, which still retains some of the phospholipid, they could see at least 2, but 2 particularly nice phospholipid residues in there. So that, again, was something that people had tried to be many groups had been trying to crystallize it. They got 20 angstrom resolution crystals, but with the EM it went quite rapidly. And then the third one is going back to this mitochondrial complex 1. Judy Hurst brought it over round about late 2013, and Xiaopen Zhu, who had made the protein, brought it. Vinoth took images like this, and within about 6 or 8 weeks, they had this map at about 5 angstrom resolution, contoured at 2 different levels. High contour level is the 8 iron sulfur complexes.
This is complex 1.
Complex 1, mitochondrial, yeah.
Yes.
Yeah.
Say ATPase.
Did I say ATPase? Sorry, yeah. I'm getting elderly, I think. So mitochondrial complex 1 is the first site of transport of oxidation in the mitochondria, converting the energy from redox from NADH, going down this iron sulfur chain to reduce a quinone in the membrane, and then somehow we still don't have a mechanism for it, but it's thought 4 protons are pumped across the membrane, and then that's used for the ATPase. So they went on, and actually at lower contour level you have the same detergent belt that you see in other membrane proteins, and then with about another year of work because there was some flexibility and so on, they did manage to interpret all 45 different polypeptides, and it was helped by some earlier work that Leo Sasanoff had done on a thermophilic version of complex 1 from thermophilic bacterium. It's about half the molecular weight, and that's these blue core subunits, which 16 bigger polypeptides, and then 29 of the smaller, what they call supernumerary in eukaryotic. This would be beef heart. So that's a good example. And then the last one is, this is now human hemoglobin, and this is a student, Miriam Koshai, whose PhD supervisor Radostin Danev and her department head, Wolfgang Baumeister, told her not to do this experiment on a Friday, but she ignored them, and they had one extra thing in addition to they had a nice phase plate that Danev had developed, and that gives you a little bit of extra contrast. And for small molecules, that's quite an advantage. So you can see now a little bit more detail than you saw in the picture that I showed you. And when they do 2D classes, there are individual classes, and eventually they put it into 3D with RelyOn, and they get, here's the heme group with the distal and the proximal histidine, just like you got with X-ray crystallography many years earlier, and with the helices and the 3D structure. So actually, you can do things that are mixed states, impure, flexibility, membrane proteins, right down to 64 kilodaltons in structure. And so it has also attracted the attention of the drug designing pharmaceutical industry. And so in Cambridge about 3 years ago, led by a group at Astex, which is a company in the Science Park in Cambridge that had been doing something like 20 years worth of drug development using X-ray crystallography, they came over and said, we think we ought to be getting into cryo-EM. And just recently, I think it's still just on the web only, it's not properly published, this is a paper that Pamela Williams was the leader, Haran Jyoti is the CEO of the Astex drug company in Cambridge, and this is not protein molecules that are their real drug targets. These were their demonstration projects that they felt they could. So it's published in Drug Discovery Today a few weeks ago, and they picked beta-galactosidase, one of the structures that I showed you, that it was impossible to do in 1997, and they get a really nice structure with 1 day of data collection. And in this paper, they said they collected 68 data sets on 68 days and got 68 structures, all between 2.2 and 2.5 angstrom resolution, and that's how it looks like it overall. But here are the ligand binding sites for phenyl thiogalactose, and then so 1, 2, 3 ligands, 3 different ligands bound to beta-galactosidase, and then another protein, pyruvate kinase, with 2 different ligands bound. And there is enough data, and particularly if you're in a drug company and you're used to interpreting it, they're very happy with this. And so now, 3 years later, they clubbed together and have a pharmaceutical company consortium, 5 companies. They get a day a week each, and they pay £200,000 a year. So that's £5,000 a day, and that's, roughly speaking, the real cost of a day of cryo-EM time at the moment. Hopefully get cheaper, because detectors will get better, everything will be faster. But the project has worked out sufficiently well. They've got another one now, same companies with a second one, and then they've all bought their own now. So you can see that it, is a. So in Cambridge now, we have in our lab 3 Krioses. There's 1 down in the biochemistry department. There's 2 in this pharmaceutical consortium. There's 1 in Astex. So there's 7. So if there's 7 in Cambridge, there definitely should be more than 2 in Israel. So, okay. So taking a step, taking a step back then from the individual interesting structures, we also like to follow how the world is progressing in its structural biology thing. And so here is some statistics from the Protein Data Bank. X-ray, EM, and NMR, number of structures deposited each year, plotted against, and so back in 1959, there'd be just myoglobin, although I think the PDB didn't actually start till 1974, so there'd be none in it. And so there are not many, but you can see X-ray has been absolutely magnificently growing, and now there are about 10,000 a year, but it looks like it's kind of plateaued there. NMR was about a quarter as popular, particularly for things that couldn't be crystallized, and there were smaller things in the early years, But essentially it peaked in 2007 and then it's sort of declined. And people use NMR now for other things, particularly weak ligand binding. And then the EM didn't really start till about 6 or 7 years ago, so it's beginning to grow here. And so we are interested in how things are going to go in the next 5 or 10 years. So the thing that we like to plot, because it covers up the knowledge of the details of what's happening, is we plotted the ratio of the X-ray depositions to EM, and it was 2,000 to 1 in the year 2000. That's because we didn't have field emission guns, we didn't have new detectors, and the microscopes weren't very good. The field emission guns came in and made it 500 times brighter and then high resolution and so on. So it dropped from 2,000 to 200. And this was the era when, for example, the Hongqiu adenovirus, and there were many but big things. And then the new detectors came in 2012, and for about a year, only 3 places in the whole world had them. So we were fortunate in Cambridge. There was Werner Kulbrandt had one in a Max Planck unit in Germany, and then David Agard and Yifan Chang had a Gatan. But it didn't take long. A year or so later, everybody starts to get them, and then you have a really big increase. So this is like 100, 10, and you can see it's. So we now do we do the extrapolation. So we reach parity in 2024, and we said, well, this Moore's law, the growth, exponential growth, usually it doesn't go on forever, because it's like, the world would collapse if there was too many. So eventually it plateaus. So we did wonder, could we look forward and anticipate what would happen? So we said, okay, what we'll do is we'll ask the PDB, what about structures from the LMB, since we were one of the earliest labs doing it? And here's the LMB ones. So we were, a few years ahead. So now in LMB, last year, there's twice as many PDB depositions by cryo-EM as there are with X-ray. And so we don't think we're unusual. We're just, we were ahead of the curve, and we've got detectors and so on. So we're not getting any more, but that means that this is guaranteed to continue down to at least here. So we're pretty sure about that, actually. So the bottom line is then, you can't go wrong by spending money. So you have to decide how much money to spend, but you can't go wrong. However much you spend, it's going to be really productive. Okay, so then that's basically the end of the history and so on. So if we now look forward, we do worry about why are we still not doing quite as well as we should do according to the theory. And so we've always worried about comparing the practical productivity of the method with what it should really be like. And one of the most interesting analyses came from, again, work that Peter Rosenthal and I did some 2003. This is our, let's say, recommended way of thinking about single particle cryo-EM. So the idea is this is resolution, or resolution squared, along the horizontal axis, and this is the average value of the structure factor of the Fourier components of the structures of the single particles in the ice. And so at very low resolution, all the atoms are essentially in one point at 1,000 angstrom resolution. So the Fourier component at low resolution is equal to the number of atoms corrected for the solvent. And then it fades, and then at high resolution, it's Wilson statistics. Arthur Wilson, who says atoms are random if you go to high enough resolution. Of course, they're not, but mathematically they're random, so they scatter as the square root of n. So it goes from n to square root of n, and then in between, depends on the shape, there's a shape factor, and also the atoms have a certain size, so there's a form factor. So that thick red line is what we expect to get once everything is perfect. And then because we've got radiation damage, there's a certain noise level here. That's if you've got one particle and you take pictures from different angles and you do tomography, that's your noise level, and so it crosses the signal level at a resolution of about 20 angstroms. So that says you can never, with electrons, and electrons are better than the other types of radiation, you can never do better than 20 angstrom resolution. So to do better, you have to average, and that's why we have multiple images of 10, 100. So the idea when we published this paper was you'd need about 10,000 to get the structure, but Peter looked into the statistics of what the X-ray people do, and they say, we solve our structures when we have a phase error of 60 degrees, a figure of merit of a half, and we had been using essentially a phase error of 5 degrees and a figure of merit, you know, it would be 0.99 and so on. So we recalibrated it, and then now the number of particles we expect is less than 1,000 to get to 3 angstrom resolution once all the problems have been solved. And so there, this is on this graph, it says, you know, a certain number, and then what happens in reality, the images are a bit blurry. We haven't solved those problems yet. So the Fourier components fade more rapidly than they should in a perfect microscope. And then in the computer program, even with rely on, there's an error bar on the angles that you've determined for the orientations of the particle. So there is an extra loss of information from lack of knowledge of the orientations. And we call that the computational B factor from the bad images. And so when the signal in the images reaches the noise level for 1 million particles, you have a certain resolution. And in 2003, we didn't have all the advantages of all the new technology. So when Peter did this on a real specimen, this is this pyruvate dehydrogenase, this is the real data coming down, and this is the noise level here. And then here we have it was 8.7 angstroms resolution at that point. And it was, you know, the idea was you should sharpen it, and so there were lots of statistics that says it seemed to be all okay. But the one thing that I'm doing a little advertisement for Peter here, we call the next graph the Rosenthal plot. And so Peter, you know, we thought at the time it was a bit of a joke really, but actually it turns out to be very useful. So the idea was in 2003, Peter had 3,600 icosahedral particles, so that's like 200,000 asymmetric units, which is that open symbol here. So that's 200,000 asymmetric units with a resolution of 8.7. So this is the experimental data in 2003. And that black dot was our hand-waving theory that I showed you a little bit earlier. So it wasn't too bad. But the B factor, the blurring factor, was 1,000. That's the same as the 3,000 for Dubochet and the 300 for Hongshou. So the idea was, if you wanted higher resolution, you could easily do it. You just carry on working. And instead of 3,600, you'd go to 100,000, 1 million, 10 million, so on. And then after many years of work, you'd have reached 5.5 angstrom. We said, no, this is a bad idea. It'd be much better to improve the methodology so that instead of a B factor of 1,000, you have 500. And in 2003, the best we could imagine was a B factor of 125. And then the idea was you'd go out here, and when you came down to your, you know, you'd have 3 or 4 angstrom resolution. So that was the goal. But actually, it's worked better than we imagined it could do. And so here were 3 examples from data sets 2 or 3 years ago. This is from Radostin Danev with a phase plate, the same one that was with Miriam Koshai. But this is on proteasome, which is 14-fold symmetry. So easy to orient, it's a favorable. So they got with 100,000 particles, which is 1.4 million asymmetric units. They got 2.3 angstrom resolution, and by putting in less particles, you get lower resolution. So, you know, more particles higher, less particles. And the fact that that's a straight line when you plot the log of the number of particles against the resolution squared, that straight line tells you that one B factor explains the behavior of the whole data set. And the B factor is 100. So that's a little bit better than we imagined was ever going to be possible in 2003. And so these are 2 other data sets. This is with a phase plate. These are not with phase plates. These are from Vinoth Kumar's work. This was a B factor of about 90 and about 122, 2 different structures. So that was a way of looking at how we're doing and looking at the progress. And then we can now look forward and say, what are we going to look for next? But before I do that, I'm going to show you one other graph, which is in these movies that you get with the new electron detectors, you can, after you've determined the structure roughly, you can look back and ask, where did the information that determined the structure come from? Did it come from the first frame of the movie, or the last frame, or the middle frame? And so this is information in each frame of the movie. This is the dose here. Either information from Relion in terms of a B factor, or we had another type of Fourier shell correlation at a certain resolution. And what it showed is that although the first image should be magnificent because the structure is completely undamaged. The first image, this is now 2 or 3 years ago, is really bad, and then it gets better, and then there's a sort of plateau, 5 to 10 electrons per square angstrom, and then you get radiation damage coming in. And it doesn't matter if you change the dose rate from 1.5 electrons per square angstrom, this is 5 times less dose, you get the same kind of graph. That was the complex one. Virtually any specimen that you do looks at the same. So the idea was to understand why it is that the best part of the image isn't working well, and then to try and address that problem, fix it, and then hopefully everything would get much better, you know, less work, higher resolution. And then I was going to show one other structure, which is a really nice one. So when we started to do this single particle, from changing from Sriram Subramanian was on his sabbatical, which became a 2-year and then a 3-year sabbatical, and then he actually resigned and went somewhere else afterwards. But he started to do single particle EM, and his postdoc artist Sawi et al. They published a paper 2015, beta-galactosidase at about 2.5 angstrom resolution, and he put all his data into public. And so now everybody with new software, they download those data and they try and do it better. And actually, now everybody has done it better than they did it. So this is Shaw's downloaded it and used it on RelyOn, and then here is the Rosenthal plot applied to this very good data set that they spent a lot of time collecting it. And you can see the B factor is 90 now, and it behaves like a single B factor. The movie frames with information content, it still loses a lot at the beginning, just like everybody else. But this is an interesting one here. So in RelyOn, when you look at the information from the different frames here, you get not only a B factor describing how much blurring there is in each of the frames of the movie, on average, but you also get an intercept back at low spatial frequency. And that tells you that's sort of independent of the B factor. And so it's scaled to be roughly 1 at the beginning. And you can see that the contrast in the image is fading. And that's because as you irradiate the sample, it's a protein molecule in a thin film of ice. You're breaking bonds and turning the protein into dust or into gas. So it turns into hydrogen gas, oxygen gas, nitrogen, methane, ethane, and that evaporates. And so at the end of the exposure, say down 30 or 40 electrons, you've lost about 1/3 of the mass of the material. Yet you still see the particles. They're just a bit blurry and they've lost their mass. And so it's amazing to me still that at the end of this, you know, you can still extract information about the structure, but we're still very interested in the part at the beginning. So then we ended up with this. What are the problems that we still needed to address? This is 2 or 3 years ago, and we were always worried about charging. Because you put the beam on it, you knock electrons out, it gets positively charged. We were worried about the fact that it's an insulator, and it sort of twinkles if you defocus it a lot. It's called B-swarm effect. Of course, you have radiation damage and blurring and so on. These were other things. But we're also worried that when you put the beam on it, water gets radiation damage and it moves around. And so we're worried about motion of the molecules, mechanical motion as well as charging, due to the relaxation of the stresses when you freeze it, and motion that's induced by bond breakage and the hydrogen gas and all this sort of. So these are all the things that we're worried about. And I'm not going to, but we've been investigating them, particularly a new group leader in Cambridge called Chris Russo. We've been working for 2 or 3 years now to address some of these problems. And I'm just going to show 2 of them that we think are quite interesting. So one of them is to do with charge buildup. So here is an image of a thin film, a carbon film with holes in it. These holes are 0.6 microns, and it's got a thin film of ice made by the Dubochet method. And this is an image at low mag before we've taken our high resolution image on it. And so you can take the high resolution image, and then you get the particles, you find the structure. If you then look at your specimen after you've taken the high resolution image again at low resolution, it looks like this. So that is happening on every single picture that you take, even though you're getting a high resolution structure. So what's happened is that the beam has been put on the middle here, This is about a micron, 2 microns in diameter. And the beam has knocked out some of the electrons of the specimen, made it slightly positively charged. And so that's why it's black. The electrons go through it, it's positively charged, and we've defocused it so that positively charged areas look back. And where did the electrons go? Well, they went all over the microscope, but some of them went out and they landed on the specimen a few microns away. So these white things, that's the electrons come out of the bit you're irradiating and they land all over the specimen. And this is now positively charged. These are all negatively charged, and so you get white dots and black dots. So this is saying that it's a real problem, and that was one of the reasons that early on we wanted higher and higher voltage in the microscope, because it would be, it turns out this is about 1 volt, and these are about half a volt on the specimen, and that wasn't there at the beginning. So you've got this gradient, and that could have been the killer in limiting your resolution, but it turns out the voltages build up very quickly, and that's all over before your first image, actually. But it was a problem, but now that we know the level of the charge and the kinetics of it, we know you don't need high voltage, you can go for lower voltage. Okay, so another one is, and then this one, so this one is going to be, I'm going to just show you this one. So this is a somewhat higher magnification, I think it should be on a loop. So here's the carbon film, here's the ice, and what we're doing is we're taking the same low mag image in, but in between each frame, a high mag image has been taken, like the one that you took. So if you look in the middle, so let me just, I'll stop it and then do it by hand. Okay, so you come along, so that's before it was exposed. That's one typical image taken, and you can see that the beam has been used to irradiate that part. The ice has got a bit thinner, and you've got a little bit of bubbling from the hydrogen gas. If you go a little bit further along, you go further and further here. I have to go further and further along. And you'll see in the hole, about now, you see a little black area here. That's because the water molecules are moving around, and that's formed a little ice crystal, and this is the diffraction spot from that little ice crystal. And if you keep going a little bit further, it changes and changes and changes and changes. There's the ice crystals bigger, and then eventually the ice, which is being lost a little bit for each exposure, eventually it gets to the stage where it pops, and then it's all gone. So you've lost all your ice, and that's happening in all of the images that you take. So the water molecules are moving around, and we always wondered how much are they moving around. You see it at a kind of gross level, but this one shows an experiment that Greg McMullen and Vinoth did, showing an image of pure ice taken at high magnification with the contrast that you get it. And what you see on the left, that is the diffraction pattern of a typical image. On the right is the diffraction pattern calculated in a different way. So instead of adding the images together and then calculating the diffraction pattern, you calculate the diffraction pattern of each frame and then add them together, and it's brighter. And the reason for that is that between each frame, the water molecules have moved. And we wondered how much they moved, so we've got these controls. So this is an image taken under identical conditions and with the two halves identically of a carbon film, and you just take the images. And now the right-hand side is faint, left-hand side where you're adding the frames together that's because in this image of carbon, the atoms of carbon have not moved. And so when you add together the frames, you're building up contrast. Whereas on the right here, we've taken exactly the same images, but each frame we move to a different area. And so on the right, it's very faint on the left and stronger, just like it is with the ice. And so you can then treat these three sets of data by averaging the frames before you calculate different numbers of frames. So here is the number of frames in the average, and there's none, so you get a certain contrast. But for the carbon film, where the atoms didn't move, that's the middle one, the more frames you add together, the more contrast you get. Whereas here, where the atoms have all moved, 100% of them have moved because we made it move, here it gets fainter and fainter as you average them. But the ice image goes like this, or like this, depending on what the dose is per frame. And so initially, the ice is following this line because for a low enough dose, essentially they don't move, but at a high dose, they all move. And so the bottom line is that every time you expose by 1 electron per square angstrom, roughly speaking, all the water molecules, the oxygens in it, move by 1 angstrom. And this could have been a real killer. In other words, it's moving the particles because you get Brownian motion pushed around, but it turns out that for a ribosome, at the end of your exposure here, it's moved by about half an angstrom. And so that's slightly blurring your images, but not enough to kill you. And smaller proteins move more, but again, it's an interesting factor, but it doesn't kill you. So we're now in the situation, we know what all the different factors are, and they're all interesting, they're all good physics, but they don't matter so much. So we've got this graph, which we call this the grand scheme to try to explain everything. And the idea is, once we've fixed all these problems, this is how it will be. Limited only by radiation damage. The first image will be perfect. The last image, after 25 electrons, will have a B factor of about, we think it's about 150. And we're working towards that, but the images that we've been getting at least 2 or 3 years ago were like this, and they were affected by water, charge, specimen buildup, and so on. So the bottom line then is that the only thing you can't get rid of is the radiation damage, but probably all the other things could be fixed, and you can make better and faster detectors and so on. And that meant that 10 or 15 years ago, we had these big B factors and low-resolution blobology. 3 or 4 years ago, we had B factors down at about 100, which was better than we imagined in 2003. But now, there are structures that are being 45 and 50. And we think that once everything is fixed, you'll get down. You'll never get below 30, because you still have to take a picture. You still get radiation damage. But the bottom line is it's going to get better. And there are a few other things, like liquid helium, chromatic aberration correctors, that I'll just mention in the last 2 or 3 slides, that might make it even better. So that's, you know, an analysis of the problems where we think we're going. But the last thing I'd like to do is just show you in a review, the same review that Vinoth and I wrote, showing pretty pictures to encourage people. We also put in a special section that was directed towards the electron microscope manufacturers. And it's called The Desperate Need for Affordable Cryo-EM. And so we had all this thing. National or international facilities are fine, but actually everybody needs one in their own lab. Otherwise, how can they work out how to make the specimen? So you want daily access. So basically every student needs to get on every day if they're going to make progress. And our idea was, particularly for smaller proteins, you need a field emission gun. You could probably manage perfectly well with 100 kV, because we now realize the charging is important. You can measure it, but it's not a killer. So we wanted it for various things, but diagnostics, specimen development. So the bottom line was, we recommended, this is now written in 2015, 5 years ago, 100 kV microscope with a field emission gun, so you get the coherence, and then a detector that works well at 100 kV. And that's, we left it, and we said, okay, well, surely the companies will read this, and they'll just make one. Nothing could be further from the truth. They read it, and they say, oh, cheap microscopes. Ah, no, bad idea. So then we carried on, and then another paper, which was now with Chris Russo, was we thought we'd investigate whether it's worse at 100 kV than at 300 kV, looking at the basic physics. And so going back in time, and there's both earlier Nobel Prizes, Bloch and Betty, had theories of electron scattering, elastic and inelastic. And so in the literature, back 50 years, there are inelastic cross-sections for the interaction of electrons with atoms, and there are elastic cross-sections. And these 2 lines here are the cross-sections from the literature. So at very high energy, the elastic cross-section is constant. The inelastic goes up because there's various, and there's what's called minimum ionization point, about 1 MeV for electrons. Below that, you get more bond breakage and ionization. Above that, you get more. So there's this minimum here. But the 2 lines also, on a log scale, they get closer together. And so as you go to lower energy, the ratio of elastic, which gives you the beautiful images, to inelastic that does the radiation damage gets better. So actually at lower voltage, it gets better. But on the other hand, proteins are a certain size, you have to penetrate them, and at 1 keV, the electrons don't even come through the specimen. So what we've done here is we've created this called information coefficient, which is the transmission with a certain information, transmission times the ratio of elastic, and that's these dashed lines here, and that's for 1,000 angstrom thick specimen, 300 or 100. And normally, so ribosomes are about 250 angstroms. Almost everything you're interested in for single particle work, you can do in a thickness of 300 angstroms. So we thought 300 angstroms for this information coefficient goes here, and here is the best place for it. And you look at it, it's 100 kV. It's not 300 kV. So we said, okay, publish a paper. Surely they will read this paper. And, so then, anyway. And then people said, well, surely 300 kV is better. So it is better for thicker specimens. But for single particles, the only reason you'd want 1,000 angstroms, you'd work in a really big virus. And actually, you don't care for big particles. They're so overdetermined. You could easily use, so actually, for all single particle work, you don't really need high voltage at all. Tomography, there is an advantage there. So we've got here, this is the arguments for it, that it's inexpensive. The theory says it will be better. We have the experiments measuring the elastic and inelastic. That was the theory, but we actually made measurements and published a paper and so on. And then there were other reasons. For example, we said to Bob Glaser, we're beginning to think 100 kV might be better. And Bob said, no, no, no. He said, if anything, we want higher voltage because of the E-volt sphere curvature. But it turns out you can correct that from the images. And Niko Grigoriev had already put that into his program back in 2006. It just never worked because the data wasn't good enough. And so Chris and I persuaded Shores to put it into Relion. So now Relion and System both have this in. You just tick the box. And then you don't need 400 kV. And then so we've got the two papers. One is on the elastic and inelastic, and then we thought we'd better do some actual experimental work to determine it. So one thing is 300 kV is still better than 100 kV for tomography because the cross sections, and you get multiple elastic scattering when you get too thick. So the idea is 3,000 angstroms, you might get 6,000 angstroms. So you will want expensive high voltage microscope for tomography, or at the moment for resolutions, because the energy spread is better. If you have a 300 kV, the energy spread of the source is the same, so you get a 3 times better delta E over E energy spread. Okay, so we thought we'd better demonstrate it, and this is a detector that was developed for synchrotrons called the Dectris Eiger detector. It measures X-rays very well, but it also measures 100 kV electrons very, very well. But it's tiled, so it has these lines here. This is 256 square, but if you correct it for bright and dark field, you can get an image. This is an image of ferritin. And so we did a few structures, and that was published a few months ago. And the best one was this 220 kilodalton structure with, it's like apoferritin, and it has some helices, 12 subunits, 3.4 angstrom resolution, showing that at 100 kV with equipment that we have now that's not been specially developed for it, that it works in practice again. So the very last slide then is looking forward by, say, 5 years and so on, what are the gains that are remaining to be made by fixing all of the problems? And we got these two tables. One is for single particle work and one is for tomography. And these are the various things that would be nice to do. So one is to cure the beam-induced motion, and there are already unpublished a couple of people who've got significant steps forward, and it might well be cured, and that's blurring of the images. And at low resolution doesn't make such a big difference. We said a couple of % improvement, but at high resolution it blurs it. It's the main problem that remains is getting rid of that beam-induced motion, and the information that you need to orient the particles is in the range. Most of the information to orient them comes. So you get this factor. Danef and Miriam Koshai had this quarter wave plate. It really works well at low resolution, gives you more contrast, but there are various defects with it, which makes it slightly worse at high resolution. But if you could make it perfect, that would be an advantage. And then we've got optimizing the energy, chromatic aberration correcting so that you retain the information in the inelastic electrons, which at the moment either contribute noise or you throw them away. Liquid helium cooling, we don't know the factor, but it's a positive factor. And detectors could be improved, particularly at high resolutions. So the bottom line, we think you should be 20 times better if you fix everything than we do at the moment. That means 20 times less work for the same structure, or higher resolution, or more multiple states, and so on. And then similarly, in the tomography, it's a different thing because you're doing lower resolution. So the quarter wave plate helps you a lot in tomography because you're looking at lower resolution features. The beam-induced motion is not so important. The chromatic aberration liquid helium might help, and we think there's a similar factor, but for different reasons that are still to be gained. And then after that, once these have all been cured, at that point, all you can do is declare victory and think of something else or use it for. Anyway, so I just want to finish then. So I showed you a variety of structures from various people who've contributed them to illustrate the various points. We've been, and still have, a number of detector development projects in Cambridge with Greg McMullen and Wazi Faruqi, and these are the two people who do chip design. They were working together, but now one of them is still at the Rutherford Appleton lab in an academic environment, and Renato has his own little company now in Spain, and either of them can design a beautiful detector for you, but it is a bit expensive. And then the last one is recently, so I've been working a little bit with Chris. Chris has a student, Katerina Nedenova, a postdoc called Matthew Peat, and we're still working to make that all better. So hopefully that's given you a little bit, going back 20 years and forward 10 years. Thank you.
Thank you very much, Richard, for that very insightful talk.
Can you elaborate a bit more about the detector at 100 kV?
Yes, so
What are the challenges of making it bigger?
Yeah. Well, the way electrons interact with your specimen, protein molecules in a thin film of ice, it's the same as the electrons that interact with the silicon in your direct electron detector, or with the silver grains in plastic in film. They go in and they get scattered. So although they enter the detector at one point, each electron goes in at exactly in one point, and you'd have very high resolution if you only knew where it was. But when it goes into the detector, it gets scattered around. And the key feature in the high voltage detectors were to have your piece of silicon, which normally comes 700 microns thick. They remove most of it. They call it back thinning to give you a 30 micron piece of silicon. And then most of the electrons go straight through with only a little bit of scatter. And so you get quite good performance at high voltage with these back thin detectors. You can't go thinner than about 30 microns. So as you drop the voltage, they get scattered more. And by the time you're at 100 kV, only a few of them come out, and they've blurred. They've created, instead of a little dot, they've created a sort of 35, 40 micron sphere of uncertainty that blurs the images. So if you take, and they're very expensive, these back thin detectors, if you turn them down to 100 kV, they really don't work very well. So the proposal that we have is that instead of having a back thin detector with very thin detector layer and very small pixels, you should go to big pixels and then don't bother with the back thinning. That makes it a lot cheaper. And so it turns out that the X-ray detectors at synchrotrons and so on, they've been developed with 50, 60, 100 micron pixels already, and they've gradually gone towards counting detectors. So they actually exist. And you can buy, and the one that we used there was a Dectris Eiger detector, which was 1,000 by 500 pixels. And it cost, £60,000 or something. However, if you wanted a big one, 4,000 by 4,000, 16 megapixels, they'll sell you one, but it's very big, and it also costs 4 or 5 million for the detector. And that's fine on a synchrotron beamline, which costs 10 million, so 4 million for a detector on a 10 million, this is fine. But on a microscope, for which our target price is $500,000, you can't have a 4 million. So the idea is to use the knowledge that has been applied at the high voltage detectors and develop a new big pixel, non-back-thinned CMOS detector that would be suitable for 100 kV. And people are starting to do it, but it's going to be at least another 18 months before they're available. And then we don't know what the price will be, but we're hoping it'll be about £150,000 for the detector, £150,000 for the field emission gun, and maybe 200,000, so it'll be £500,000 is the target. And so you can get 10 of them for the price of one of the Krioses. That's the idea. Yeah, Nathan.
Okay. There are problems that we can fix because the data that is deposited in the PDB, some of them are really bad.
Yes.
So, really bad. And since we have no criterion how to do it, and since almost most of the referees don't look at them, almost none. I know because I start looking at this, I start getting papers to review, which is good. So, I think that we, the scientists, should make a cut for RMSD. Below this, don't build anything.
Yeah. No,
because if you report 2.7 angstrom resolution, and essentially all the interesting things are at 8 angstrom resolution, you cannot do it.
That's right. No. So the maps you get are often quite good.
Yes.
But if you are an X-ray crystallographer and you're moving towards solving your structure and you can see the beginning, you build the model, and if you build it with a lot of energy and insight and labor, you get a big reward, which is you build a good part of the model, you get better phases, and other parts are revealed. Yeah. So the procedure of refining an X-ray structure gives you a reward every day. Yeah. So people do it. Whereas with the EM, you've got the phases. You can't make them any better. So a large number of people, they just dump in the nearest structure. So, you know, and then they don't even bother. And then you look and they're polypeptide chains not in the density and so on. And so, but there is a community, the people who run the data banks and the validation, there are meetings now, developing criteria now, so that force people to deposit their map and their model, and then you get a report, 20-page report, just like you get with X-ray. And it's not a police force telling you you're bad. It's a psychiatrist giving you advice about how to improve your model before you submit the paper. And so things are moving in the right direction, and people are aware of it. So you know it will be improved. Yeah. So, but there are optimists and pessimists. Yeah.
Thank you. How close do you think we are to true single particle analysis? I mean, getting a structure from only a handful of single particles in a very high resolution.
I think, you know, we're quite close. So I've asked people so there are particularly favorable specimens. So Greg McMullen and I published a paper in 2014 saying you couldn't do apoferritin. And that's because we couldn't get the orientations. These were the very earliest days. We had, you know, in the Thermo Fisher, it was Falcon 1, Falcon 2. It was before we had counting and so on. And we showed, it was a paper, we said it was apoferritin, because it's beautifully spherical and has no low resolution contrast. You have to get beyond 10 angstroms to find the orientations. But now, the #1 structure for resolution in the whole world is apoferritin. So impossible in 2014. Now it's the #1 structure in the world. So I did ask some of the people who've published, I said, what happens if you take your single best image? What resolution do you get to? And it's 2.9 angstroms. So there's one image with maybe 100 or 200 particles, in one single particles, no crystals. In one image, you get 2.9 angstrom resolution. And that is apoferritin. So there's nothing wrong with the methodology. What happens with a lot of specimens, particularly membrane proteins and so on, they fall apart. And people take and then they end up with, they start with 1 million, they end up with, say, 30,000. So it's and then you don't know whether the other 970,000, are they other interesting structures that you've missed, or has your protein fallen apart? So the one thing I didn't mention actually is, because we focused on these technical things, but making that thin film, you do get denaturation at the air-water interface. And there are quite a lot of people who know this and are trying to work on it. And I can remember about 2 or 3 years ago, I asked Steve Harrison at Yale, I said, how come you're not doing cryo-EM yet? And he said, all our interesting structures, they don't work with cryo-EM. And that's because when they made the thin film, they sort of fell apart. Now, they've worked at it, people are getting around it. So one idea that quite a few people are working on is to take the holes in the carbon or the holes in the gold and to use a thin single layer of carbon, graphene, which is somewhat hydrophobic by itself, but to derivatize it with various groups, for example, nickel NTA, and then attach your protein to a specially constructed surface that would not itself denature the proteins, and then have a 300 angstroms of buffer so that the protein can't reach the other surface as you blot it. And so there are quite a few groups trying to do this. So there will be developments in specimen preparation, and in hopefully you'll just be able to buy these grids, just like you can buy a loop for doing freezing crystals for X-ray crystallography as well. So I think there's a lot of people working on it, and the good thing about the success of the method, it's pulling in a lot of clever people with lots of new ideas. So I think I'd be optimistic about it.
Anyway, thank you very much, Richard, for